Hello, can you guys hear me? If you guys can just comment if the audio is okay. If you guys can just comment if the audio is okay. All right, so we'll start. So today's lecture is on the cardiovascular system. So I believe that you guys have a heart is a muscle physio seminar coming up this week. So hopefully I'll be able to cover all the topics for that test. And yeah, if you have any questions, just ask me like during the lecture, or we'll have like a part where we can have like a question answer session at the end as well. So you can ask me questions. And yeah, I hope you find this lecture useful. So we'll start off with showing you the structure of the lecture. So first we'll start with a brief physiological anatomy and like overview of like the function of the heart. Then we'll move on to the cardiac muscle, which will cover these three exam questions. Then we move on to the cardiac cycle, heart failure, regulation, and obviously, as I said, we'll have questions at the end of the lecture. The reason why I've split up like this, because I feel it's a lot more easier to understand the heart as a whole. For example, like in the actual exam, when you do get like a question like one of these and you know it really well, it's very likely they'll actually link it to all the other questions as well. So even if you know, for example, this question really well, the frequency effect, they can ask you about like cardiac output, etc. And if you don't know cardiac output that well, then they can actually fail you on that question. So it's important to know the whole heart, like the whole heart on like as a whole, compared to just like individual questions. So it's better to like link the questions together like this. And also, talking about the exam, they can also link it very easily to other organ systems. So, for example, from the heart, they can easily talk about the kidneys. So, even if you get a heart question, but your kidney knowledge isn't that strong, you can still fail that question because of that. So, yeah, so we'll just start with the brief anatomy and function of the heart. So, obviously, now this is the heart. It's split up into four chambers. So, you have the two atria at the top and then two ventricles at the bottom. The heart is a double pump, so meaning that the right side pumps blood into the lungs via the pulmonary circulation, and then the left side pumps blood around the whole body via the systemic circulation. The main structures, so obviously you need to know like the inferior vena cava, superior vena cava, which have the venous return to the right atria. The blood gets then pushed into the right ventricle, which obviously goes via the pulmonary artery, the right and left branch. Then through the pulmonary circulation, it comes back to the left atria via the pulmonary veins into the left atria, and left atria then pushes blood into the left ventricle, which then pushes via the aorta all around the body. The valves that you have, so you have the tricuspid valve on the right side, which split the atria and the right ventricle, and you have the bicuspid, also known as the mitral valve, which is on the left ventricle, so it splits the left atria and the left ventricle, and then you also have the semilunar valves. Structure of the heart, so you have three layers. So you have the endocardium, which is the innermost layer. Then you have the myocardium, which is your actual cardiomyocytes, which is split into two. So I'll talk about this later when we talk about contractility, but it's split into two different types of cardiocytes. So you have the working myocardium, which is actually your contractile cells, the actual cells that contract to push the blood out. And then you also have your conducting myocardium, which is what actually conducts electrical impulses around the heart, which Ashwin mentioned in his last lecture. And then just for completion's sake, I talked about the pericardium, which is just the layer which surrounds the heart and is split into the serous and fibrous pericardium around the heart. I talked about the heart valves. Innervation is important. So you have the sympathetic innervation from the sympathetic trunk. So you just have cardiac nerves which innervate, and you have beta-1 adrenergic receptors all over the heart. And then you have the parasympathetic nerve branches from the vagus nerve, and the receptors, the muscarinic receptors, are only on the atria. There's no muscarinic receptors on the ventricle. So it only affects, for example, heart rate, and the atria cannot affect the ventricles. And then blood supply, we'll talk more about this during the coronary circulation. But it's basically split into two coronary arteries. You have the left coronary artery, which branches off the left anterior descending, and the left circumflex, and then you have the right coronary artery. And obviously the blood supply is to provide the nutrition to the actual heart. So yeah, so that's just a brief overview, just in case. I mean, obviously you probably remember this from anatomy, but just it's nice to have like an overview of the heart. All right, so we move on to the cardiac muscle. So as you know, the body has three types of muscle. You have skeletal muscle, you have smooth muscle, and you have a third type, which is cardiac muscle. And the reason why cardiac muscle is different is because essentially it is striated muscle, but it has a smooth muscle property, which is the fact that all the cells are linked together in one syncytium. I'm not sure if I'm pronouncing that right, but what that means is basically they're all connected via these intercalated discs, which are basically gap junctions, which lower the conductivity or increase in conductivity between these two, all the cells. So that means that they basically can all contract at the same time instead of, so when one impulse comes through, they actually all conduct at the same time. And it's important because you want the whole heart to contract and the ventricles to contract, so it pushes blood at the same time. And obviously when it goes wrong, such as ventricular fibrillation, if it starts contracting at different times, then obviously no blood will be pushed around the body. So it's an extremely important feature. And yeah, that's what makes it different from skeletal muscle, and what it has basically a smooth muscle property. Cardiac muscle cells, they undergo excitation, contraction coupling, which I'll talk about in the next slide. And also I talked about the working cardiomyocyte versus conductive cardiomyocyte. So I'll talk about electromechanical coupling, which basically means how an action potential, which starts from the synoatrial node, which then goes to the AV node, and then via the Purkinje fibers to the ventricles, how that electrical impulse corresponds to the heart muscle actually contracting. So over here, you have the action potential, which comes down. They actually go inferiorly into the cardiac muscle via T tubules, and then they open voltage-gated calcium channels. So these are voltage dependent. When the membrane potential reaches a certain level, this is when it opens. And the extracellular calcium, so calcium in the extracellular space, it goes into the cell, into the sarcoplasm. And then the calcium then, via calcium-induced calcium release, acts upon the receptors, which are known as ryanodine receptor channels. So these ryanodine receptor channels are all over the sarcoplasmic reticulum. Your sarcoplasmic reticulum is what stores the calcium inside the cardiac muscle cell. So it has large amounts of calcium stored inside. These are like longitudinal tubules, and they have a lot of calcium. Basically, there's no calcium actually in the actual cytoplasm. The reason why it's key that you keep it like in the lipid membrane, because if you have calcium just all over the cell, it causes a lot of damage, and because it can just bind, because it's like a positive ion, so it can just like cause a lot of reaction. So it's important to keep it bounded in this lipid membrane, and it only opens when the calcium comes in, when these voltage-gated channels open, and they basically open the calcium. So that's why it's called calcium-induced calcium release, because the calcium is basically opening these calcium ryanodine receptor channels and allowing huge amounts of calcium to come out into the cell. And the calcium comes out, and then the calcium then attaches to troponin. So I'm pretty sure that you know the sliding filament model for skeletal muscle. It's exactly the same, how a striated muscle works. Calcium basically binds to troponin C, which then causes a conformational change which then allows the tropomyosin to basically also have a conformational change, which allows the actin filaments to be exposed, which allows the myosin head to basically attach and then cause the power stroke, which causes the actual contraction. The main difference between cardiac and skeletal muscle, however, is that the extracellular calcium level is actually very important. In skeletal muscle, the extracellular calcium doesn't really make much difference on how much the force of contraction there is, but the actual extracellular calcium actually makes a huge difference because it also participates in the contraction. And after the action potential is ended, and then it's time for the heart to relax again, the calcium is pumped rapidly back via Surca channels. So Surca stands for sarcoendoplasmic reticulum calcium ATPase. So using ATP, huge amounts of calcium is pumped back into the sarcoplasmic reticulum to restore the calcium stores. And then the rest of the calcium is then pumped out of the cell via these sodium-calcium exchanges. And to have this pump functioning, basically, you need to have a sodium gradient. So as you know, every cell has these sodium-potassium pumps, which means that there's a large, high concentration of sodium outside of the cell, and a low concentration of sodium inside the cell, a high concentration of potassium inside the cell. And this is important. This diffusion gradient is actually quite important because if you have a high concentration here, it means that more sodium will want to push into a low concentration of sodium here, so that means that more calcium will be pumped out of the cell. If you have a low diffusion gradient, so let's say that the sodium concentration is increased in the sarcoplasm, meaning that there's not that much difference between the concentration, then sodium wouldn't want to go into the cell, meaning that there'll be less calcium being pumped out. And this is quite important to do with contractility, which I'll talk about in the next slide. But this is basically one of the main factors which increases, because basically if you have a higher calcium store inside the sarcoplasmic reticulum and more calcium basically around, that means that there'll be more binding to troponin C, which means that there'll be a greater power stroke, which means that the force of contraction will also be increased. So this diffusion gradient is actually quite important, so you need to make sure that you know about that. This is just a brief reminder of the sliding filament model, if I wasn't clear before. The calcium basically binds to troponin C, which then causes the conformational change. This then prevents troponin I from inhibiting the tropomyosin complex. The tropomyosin basically lifts up and allows the actin filaments to be exposed. And then the actin filaments then the myosin heads can basically attach to the actin filaments and form the cross bridges. And then basically allow it to do that power stroke and then cause the contraction. So that's the sliding filament model. Okay, so we'll talk about contractility. So with physio questions and the physio department in general, they really love definitions. They really want you to just say the basic definitions just to show that you actually understand it. And you're not just talking about details and just talking about very specific points. They want you to see if you actually understand it very well. And the way they see that somehow is they want you to define it. What is it? Basic terms. What is contractility? So contractility is just the ability of the cardiac muscle to be able to contract. If the muscle is able to contract, it has contractility. If it can't contract, then it has zero contractility. And then inotropism. So inotropic is actually the influencing the force of the muscular contractility. So if you contract with a higher force, you'd say that it's positive inotropism. And when I was studying, back when I was studying for the physio exam, I used to get this word mixed up with ionotropic. So it's not ions. It's nothing to do with ions. It's inotropic. So it's a different word. So make sure you don't start saying ionotropic in the exam. So basically, what affects contractility? What affects how hard that the muscle can contract? What affects the force at which the heart muscle can contract? And this can also be said in a different way. All these can be known as inotropic agents. So what are inotropic agents? The main one, which affects contractility, is your autonomic nervous system, which is your sympathetic nervous system and your parasympathetic nervous system. As you know, the sympathetic nervous system is mainly norepinephrine and epinephrine, which then bind to adrenergic receptors. And your parasympathetic system is your acetylcholine, which then bind to muscarinic receptors. And we'll talk more about how the nervous system, autonomic nervous system affect contractility in the next slide. What are other factors which affect contractility is temperature. So if you have an increased temperature, that increases your heart rate because it actually makes the membrane more permeable to ions, which means that it basically increases the heart rate and also, to a certain extent, increases contractility. I'll talk about how heart rate increases contractility later on. Yeah, so I'll talk about it because you have the frequency effect, which also increases contractility, which is to do with heart rate. But yeah, temperature only affects it to a certain extent because eventually if you have too many ions coming in, then that also decreases contractility. So that's how temperature affects it. Calcium, what we talked about, if you have a higher calcium concentration, then obviously the contractility is increased. However, if you have hypercalcemia, it can actually cause spastic contraction, so that's not good. And if you have hypocalcemia, that means that you have less calcium in your blood. That would mean that the contraction will be weaker because there'll be less extracellular calcium concentration. And then potassium. Potassium ions, as you know, also decreases contractility because there'll be less potassium ions basically decrease the heart rate via the parasympathetic system. And also it basically increases the resting membrane potential. So if the resting membrane potential is decreased to a certain extent, that means that you need a higher action potential to basically cause the contraction. So that means that the contraction itself will be a lot weaker because you need a lot more high energy action potentials. Heart rate, again, we'll talk about later. And you also have drugs. So drugs such as digitalis, which is a cardiac glycoside, it's a sodium potassium inhibitor. So as I mentioned before, it inhibits this sodium pump, meaning that then the sodium concentration inside the cell will be increased and the diffusion gradient will be decreased, meaning that there will be less sodium wanting to exchange with calcium, meaning that there will be more calcium left over in the cell, and this calcium will be pumped via circuit instead of leaving the cell. So then your calcium store inside the sarcoplasmic reticulum will be increased. This is important because when the next action potential comes, then the more calcium is readily available to be pumped out the cell and cause contraction. And if you have more calcium, then that causes a stronger contraction because there'll be more cross-bridge formation. And that will cause like a more powerful power stroke. And then one thing to note, so increased contractility causes increased stroke volume. So if you have an increased force of contraction, it's able to push more blood out of the heart. And then if you have an increased stroke volume, because cardiac output is equal to stroke volume times heart rate, that means that increased stroke volume will increase your cardiac output. But again, we'll talk more about this during the cardiac output, or when I talk about the cardiac output. So as I mentioned, the effect of sympathetic nervous system. So this is the main effect for contractility. So sympathetic nervous system, obviously, norepinephrine. It binds to beta-1 adrenergic receptors via GS, the G-coupled proteins. This then activates adenylate cyclase, which is an enzyme located on the membrane, and then via this pathway, ATP is converted to cyclic AMP, which then activates protein kinase A. Protein kinase A phosphorylates, so it phosphorylates phospholamban, L-type calcium channels, and troponin. So phospholamban is an inhibitor of the SERCA channels. So these are the SERCA channels. Phospholamban basically inhibits these. So you have quite a lot around the sarcoplasmic reticulum, and then some of these will be inhibited by phospholamban. Sympathetic nervous system, basically, or protein kinase A via sympathetic nervous system stimulation, phosphorylates phospholamban, meaning that these channels will remain open. So the inhibitor, it basically inhibits the inhibitor. So that means that more of these channels will be open. So that means that if there's more circular channels open, that means that more calcium will be able to be pumped into the cell, and then that increases the calcium concentration inside the sarcoplasmic reticulum. And again, as I said, if you have a higher calcium store inside the sarcoplasmic reticulum, that will mean that there will be more calcium readily available for the contraction. So that also increases contractility. L-type calcium channels. So basically, the calcium channels on the membrane, it basically phosphorylates them, keeps them open. So that means, again, there'll be more calcium rushing into the cell. So it'll be increased calcium from extracellular to intracellular. And it also phosphorylates troponin, so meaning that it will be more sensitive to calcium. So if calcium can bind readily to troponin, that means also there'll be more cross-bridge formation, and that will also increase contractility. The sympathetic nervous system is kind of important. It has a positive lusitropic effect. What lusitropic means is the rate at which the heart muscle can relax, how quickly it can basically go back, like how quickly the heart muscle can relax. Why this is important is because if you have an increased lusitropic effect, I mean, the way the sympathetic nervous system increases lusitropic effect is by phosphorylating phospholamban, because if you have more circular channels open, it means that the calcium can rapidly move into sarcoplasmic reticulum compared to if you have only one or two here, and it's just like slowly putting these calcium into the sarcoplasmic reticulum. That means that if you have a lot more open, that means that the calcium concentration in the actual sarcoplasm can decrease rapidly, ready for the next action potential. And this is important because if you have a lot of calcium just randomly around the cell, or if they're like moving out of the cell, and then the next action potential comes, and there won't be as much calcium ready for another strong contraction. But if you have, if the calcium is rapidly put back into sarcoplasmic reticulum, and the next action potential comes, that means there'll be a huge store of calcium ready for next contraction. And that's why a positive lusitropic effect increases the contractility as well. And this, just to summarize, so increased calcium ions means more troponin binding, which means more cross-bridge formations, which means a greater power stroke, and therefore an increased force of contraction. Okay, and then we'll move on to the Starling principle. So, as you know, every single muscle tissue has something called the length-tension relationship. What that means is that every single one of your muscles is at a slight tension, because this would produce a greater force compared to if it was completely like flaccid, if it was completely like no tension whatsoever. The reason why this is because if you, so I basically made this little sketch here, just like trying to explain a little bit better. But basically, if it's not stretched, if there's no tension, if there's no stretch to the muscle, then the actin filaments, they overlap over each other. And if this is your myosin head, if this is myosin, these overlapped parts of actin filaments, the myosin heads, they can't attach to it, and then there's not much space for the contraction to occur. So if you think about the contraction occurring in this direction towards the midline, there's not much space where they can actually contract. Whereas if they're stretched a little bit, if the actin filaments are stretched a little bit, then there's more like spaces where the myosin heads can attach to. And if there's more spaces where the myosin heads can attach to, they can cause a greater force of contraction compared to if they were just here. And even if you have more stretch, then that would also increase. So there is an optimum where there'll be a greatest contraction, or greatest stretch where it can be a greatest force of contraction. However, obviously there will be a point where there will be too much stretch and then the contraction, because if the actin filaments are stretched too much, that they're so far away from these myosin heads that there's only like a few that they can attach to, then obviously then the force of contraction will also decrease. And the way I like to think about this is think of an elastic band. If you stretch an elastic band a little bit, then the force that it comes back together again is only a little bit. If you stretch a little bit more, then it increases the force at which it just snaps back together again. However, if you stretch it too much, then there's a point where it loses elasticity and you just get stuck like that, you know? So that's how I like to think about the length-tension relationship. So this is actually important for the heart, because it's known as the Frank-Starling law. So what the Frank-Starling law is, basically uses the length-tension relationship to mean that the heart is able to regulate itself very rapidly and is able to adapt to different changes to the amount of blood returning to the heart. So it basically states that the stroke volume of the heart increases in response to an increase of volume of blood in the ventricles before contraction. What that basically means is that when you have an increased venous return, your venous return means that there's more blood coming back into your right atria from the superior vena cava, from around your body. If you have an increase, like a slight increase of blood coming back, that means that there'll be more blood in the left ventricles, and this will stretch the heart muscle, the left ventricle, a little bit. And because of the stretch, this means that there'll be a higher contraction or increased contractility, which means that there'll be a larger force, which means that there'll be more blood which will be pushed out the heart. So this basically means that this is known as autoregulation, meaning that it's the mechanism that allows the cardiac output to be synchronized with the venous return. Autoregulation basically means that the heart is able to regulate itself. So autoregulation means regulation of itself. And this is important for because obviously the sympathetic nervous system is what regulates the heart, or the autonomic nervous system. However, you do need small adjustments which the sympathetic nervous system won't have enough time to react to. For example, let's say you start exercise. That moment when you start exercise, you have the muscle pumps at the bottom of your legs, which then contract and push the blood up into your heart via the superior vena cava. That means that there'll be more blood in that one heartbeat. There'll be more blood coming in to the heart at that point. How do you, to prevent pooling of blood in the heart, to allow all the blood to be pushed out, you need to increase the contractility at that instant. So the way the heart does this is because of that length-tension relationship, because it's stretched a little bit more, it's able to push at a greater force. And it also works the opposite way as well. If you have a decreased venous return, for example, when you go from a lying position, a supine position, to a sitting or standing position, your blood actually just drops because of gravity to your lower extremities. Because it drops, this means that there'll be less blood returning to the heart. Your venous return will be decreased. When your venous return decreases, because there's less stretch, there'll be less blood actually being pushed out. This is actually a kind of bad thing as well, because if you have less blood being pushed out, that means that your cardiac output has been decreased. And this also is the reason why when you go from lying position to standing up too quickly, it actually causes you to feel a bit faint, start fainting a little bit, because there's less blood going to your brain. But yeah, so this is the Starling principle. The reason why it's called heterometric is because it's due to the difference in the size of the muscle, whereas the frequency effect it's nothing to do with how much the muscle stretches. It's more to do with the heart rate. So yeah, so do you guys understand the Starling principle? If you have any questions, just let me know if you don't understand a certain point. All right, so then we'll just move on. Okay, so then we'll talk about the frequency effect. So the frequency effect also is the heart's ability to increase contractility and restore stroke volume when afterload increases. What it basically means is that when the heart rate increases, it's able to increase contractility. The reason why it does this is known as the Bowditch / staircase phenomenon. The reason is that when you have heart rate, when your heart is beating fast, there's not enough time. Your diastole gets decreased rapidly, so there's not a lot of time for the heart to relax and allow the calcium to slowly move out of the cell. It just stays in the cell and gets rapidly put into the sarcoplasmic reticulum instead of leaving, because it doesn't have enough time for the sodium-calcium exchanger to work, basically. So there's more calcium left over after every heartbeat, and you can see it just goes up in a stepwise fashion. So that's good, because if you have an increased heart rate, you need to. The reason why your heart rate has been increased is because the body realizes that you need to increase the cardiac output because the body needs more oxygen and more blood flow. So it's good that if you have an increased heart rate, you increase the contractility and therefore the amount of blood that you're pushing around the body, because that also increases the cardiac output. So yeah, basically contractility, the tension, increases in a stepwise fashion. So if in a normal heart rate, you have enough time for relaxation, so the calcium ions to leave the cell, whereas when the heart rate increases, because you have less time for relaxation, the calcium ions just accumulate over time, and then that basically increases the contractility. You also have something called the unrep effect. So this is basically when the heart muscle is like at a sustained period of tension, as it is when the heart rate is increased, it basically activates tension-dependent sodium-hydrogen exchanger, like the exchanger, and that basically increases the intracellular sodium concentration. So as I said before, if you increase the sodium concentration, that would mean that the diffusion gradient between the outside and inside of the cell will be decreased, meaning that there'll be less sodium wanting to move in, which means that there'll be more calcium left over in the cell for a greater contraction. So this is how the anaerobe effect works. It basically activates these sodium-hydrogen exchanges, these sodium-hydrogen pumps, basically, sodium-hydrogen pumps. And it lowers the diffusion gradient and then less calcium exchange out of the cell via the sodium-calcium exchanger. So that's also another way that the heart regulates itself when there's increased heart rate. This is known as the frequency effect. So these two are the two autoregulated factors of the heart, the Starling principle and also the frequency effect. All right, so now we have a question. So which of the following agents or changes has a negative inotropic effect? So as we discussed before, inotropy is basically like the force of contractility, the force of muscle contraction. So which of these answer options basically causes a negative force of contraction? What weakens the contractility? So I'll just give you a moment to answer it. Yep, so the answer is D, acetylcholine. So the reason why is because increased heart rate, as we discussed, because of the frequency effect, increases contractility. Sympathetic stimulation, obviously, we talked about how sympathetic is the main factor for increasing contractility for the heart. Norepinephrine obviously works via the sympathetic nervous system, increases contractility. And cardiac glycosides was the drugs, the digitalis drug that I was talking about before, which was the sodium potassium inhibitor, which also increases contractility. So acetylcholine works via the parasympathetic nervous system, and obviously the parasympathetic nervous system is what decreases the contractility. So I hope that was clear for you guys. And then the second question, so Starling's law of the heart. A does not operate in a faint heart. B does not operate during exercise. C explains the increase in heart produced by exercise. D explains the increase in cardiac output occurs when venous return is increased. And E explains the increase in cardiac output when sympathetic nerves supplying the heart are stimulated. So I'll give you a moment to answer that one as well. So the answer is actually D. The reason why is I'll explain it. So it does not operate in the failing heart. It does because it doesn't have anything to do with the nervous system or anything like that. It's to do with just the muscle tension, because it's to do with how much the muscle stretches. So during a failing heart, when you have increased preload, or I'll talk about preload later on, but if you have increased venous return and you have a higher stretch, then obviously that will increase contractility. Obviously operates during exercise. So this statement is wrong, because if you have, as I said, if you start exercise, you have increased venous return, that rapidly just increase the contractility as well. C explains the increase in heart rate produced by exercise. So the Starling's law has nothing to do with heart rate, because the heart rate is primarily affected by the sympathetic nervous system. So Starling's law is not to do with that. D explains the increase in cardiac output that occurs when venous return is increased. This is what I've been talking about when I explained the Starling's law, is that small changes in the venous return is primarily what the Starling's law is for, meaning that if there's an increase in venous return, the contractility is matched to that. And E explains the increase in cardiac output when sympathetic nerves supplying the heart are stimulated. The reason why cardiac output is increased when sympathetic nervous system is innervated, or sympathetic nervous system is stimulated, is because it increases the contractility and it also increases the heart rate, and then basically increases stroke volume and heart rate, so that increases the cardiac output. So that's not to do with the Frank Starling law. So D is the answer. All right. So now we'll actually move on to cardiac output. So cardiac output. Also, one thing I forgot to mention. So you have to be careful about the wording of the exam question. So when I was studying during my exam, this question used to really annoy me, because I was just like, cardiac contractility and its determination. Like, what does determination mean? And I assume, like a lot of the documents as well, they assume that determination means that it's actually how contractility is measured. But I'm pretty sure that's not the case. I think when it says determination, it just means that what affects contractility of. So this question is basically asking you to describe what contractility is and also describe what affects contractility, and that's what I did. Whereas if it actually specifically says in the question and its measurement, this is when it actually wants you to state how cardiac output is measured. So that's one thing to note. So cardiac output is equal to stroke volume times the heart rate. Stroke volume is basically the amount of blood which is pushed out of the heart every beat. So your normal, for an average person, your stroke volume is about 70 milliliters per beat, and your average heart rate is about 70 beats per minute. So if cardiac output is stroke volume times the heart rate, it corresponds to about 4,900 milliliters per minute, this is about 5 liters per minute. So your heart is basically pumping 5 liters of blood every single minute, and this is your cardiac output. The cardiac output is a good parameter because it indicates how the heart meets the body's demands. So for example, if you start exercising and your muscles basically are working harder and they need more oxygen, then obviously the heart needs to meet this demand. It can't be pumping at the same time, at the same rate at rest, because the body needs more oxygen. So the cardiac output is basically a way how we can measure how the heart is coping with the excess body demands, basically. And one thing to note is that, for example, in athletes, the cardiac output can be significantly increased. So it can be almost up to 30 liters per minute, with like the max cardiac output, whereas for normal people it's a lot lower. And obviously with people with like heart pathologies, etc., their cardiac output is even lower. So cardiac output is really good on the wards and stuff, because if you can measure it, then you can measure how well the heart is functioning, or if the person's undergoing heart failure. So how do we affect cardiac output? Because it's a simple equation, there's two parameters. Like to increase cardiac output, we can either increase stroke volume or we can increase heart rate. So what affects the stroke volume? there's three factors which affect stroke volume. It's your preload, your contractility of the heart muscle, and your afterload. So your preload is how much blood is coming into the heart before every heartbeat. So this is primarily your venous return. So if your venous return is increased, then that means that your preload is increased. And this also, preload is also known as basically the end diastolic volume. So what your end diastolic volume is the amount of blood in your heart before ventricular systole. So at the end of diastole, it's basically the volume at the end of diastole. And then this is your end systolic volume. So this is the amount of blood that's left over after the heartbeat, after the ventricular contracts, basically. And to work out your stroke volume, you basically do end diastolic volume minus end systolic volume. And your end diastolic volume, so the amount of blood left at the end of diastole after your heart is filled up, is about 120 milliliters. And your end systolic volume is about 50 milliliters. So if you do 120 minus 50, you get about 70 milliliters, which is your normal stroke volume. Contractility also affects stroke volume. So I didn't explain how venous return. So the reason why preload affects stroke volume, because if you increase in your end diastolic volume, obviously you're increasing your stroke volume. And also because increased venous return via the Frank-Starling mechanism increases contractility, it also increases the amount of blood that gets pushed out. So, and then also you have contractility. So if your heart is pumping out greater force, it's able to push more blood out. So that also increases how much your stroke volume. And then your afterload is the resistance at which the heart has to overcome to push blood out of the heart. And this is basically your total peripheral resistance. And it's also, so basically you want this to be very low to increase your stroke volume, and you want this to be very high to increase your stroke volume. Because if you have a high afterload, it means that the heart has to work a lot more harder, and that means it will push a lot less blood out compared to if there was like hardly any resistance, then the heart could push a lot more blood out. And what affects afterload? I'll talk about this later when we talk about preload, afterload. It's basically stuff like hypertension, your blood pressure, aortic stenosis, if you have those heart pathologies, or if you have atherosclerosis and basically your heart vessels lose its elasticity, then these all increase the amount of resistance that the ventricle has to overcome to push blood out. So to increase stroke volume, you need to make sure that your afterload is very low. And then what affects heart rate? So this should be very simple. It's obviously your autonomic nervous system. Your sympathetic nervous system increases your heart rate, your parasympathetic decreases your heart rate. Your thyroid hormones, so your T3 and T4, they also increase your heart rate. Temperature, as mentioned before, higher temperature increases your heart rate. And also, main factor is also your stimulation of your peripheral chemoreceptors. So in biochem, you'll learn about, or you probably learned about already, about how, like during metabolic alkalosis, metabolic acidosis, your peripheral chemoreceptors can be activated and then activate your respiratory system to compensate. But they also, as a side effect, also affect the heart rate. So if the body detects that you have increased CO2, so you have more CO2 in the body, then this will also increase your heart rate. And then this is the ways that you can measure cardiac output. So one of the main ways that cardiac output is measured is via ultrasound, via the Doppler method. So I'm not sure if you remember biophysics, but the Doppler method basically allows you to measure both the velocity and volume of flow through like a artery, or in this case through the valves. And this basically gives us the stroke volume, because if we're able to measure how much blood is flowing through a certain part of the heart at a certain given time, then we obviously know what the stroke volume is after every beat. And if we know the stroke volume, then we can easily work out the cardiac output, because if we know the heart rate, if we hook up the ECG, then obviously we know the heart rate. So it's very easy to work out the cardiac output, because you just do stroke volume times the heart rate. So that's one way of measuring cardiac output. The other method, which is a bit more complicated, is the fixed principle of measuring cardiac output. Fick's principle relies upon measuring the O2 consumption using one of these like spirometers, and it measures how much O2 is being consumed like how many milliliters of oxygen is consumed per minute. It also measures your arterial blood, the oxygen concentration in your arteries, and also measures the oxygen concentration in your venous blood when it goes back to the heart. And the simple equation is that the cardiac output is equal to the oxygen consumption from the body divided by the arterial concentration of oxygen minus the venous oxygen concentration. So if we work out like the normal cardiac output, so if we assume that the O2 consumption is 250 milliliters per minute, and the arterial concentration is about 19%, meaning that for example, or 19% basically means, so for example, if you have 100 milliliters of blood that you collected, about 20% of that, or 19% of that would be oxygen. So in the 100 milliliters of arterial blood, about 19 milliliters would be oxygen. And then you also have a venous blood, which is about 14% concentration. So if you want to work this out, so then you do 250 divided by 0.19 minus 0.14, which is about 0.05. So you do 250 divided by 0.05, which comes out to about 5,000 milliliters, or otherwise known as 5 liters per minute. So that's the way that the uni actually wants you to be able to work out oxygen. So this could be a question in your report, which could be just work out using Fick's principle, work out what the cardiac output is using, then they'll give you these parameters. So to practice that, I've also added a question. So during exercise, a man consumes about 1.8 liters of oxygen per minute. The arterial oxygen content is about 100 milliliters, and the oxygen content of his mixed venous blood is about 134 milliliters per liter. His cardiac output is approximately, so this is what you need to work out. So make sure that you convert the 1.8. So this, like when you get questions like this, you have to also always make sure about the units. So make sure that you have all the units the same. So change the 1.8 to 1,800 milliliters. So then you do 1,800, and then using these two values and adding to the equation, you can work out the cardiac output. So I mean, I'll give you a few minutes or a few moments to work out this answer. That's another thing, that you should always bring a calculator when you come for the physiology final. Yep, so the answer is C, 32 liters per minute. So if you added all the parameters to the equation properly, that's the answer that you should get. All right, so now we'll talk about the cardiac cycle. So just a brief overview, so you know like what one cardiac cycle, I mean obviously you know, but I'll just go over it. It's basically blood enters the right ventricle, sorry, not the right ventricle, the right atria, which then after atrial systole moves in via tricuspid valve into the right ventricle. The right ventricle then contracts and then pushes blood via the semilunar valves in the pulmonary trunk to the pulmonary the pulmonary blood then after it's basically from deoxygenated to oxygenated in the lungs. After oxygenated blood then comes back via the pulmonary veins into the left atria. The left atria then contracts, and then it moves in blood into the left ventricle, and then left ventricle then contracts, and then basically pushes blood out of into the systemic circulation by the aortic valve. And basically the pressure volume loop is basically just that one heartbeat. It basically explains it, but there's a little bit more phases than you might know already. I think Ashwin went over this when he talked about polygrammetry in the last lecture. This is basically like a graph that you need to be able to draw in the exam when you get this question. Any of the graphs that I've mentioned in this lecture as well, they actually want you to be able to draw it. And it's actually important that you know. So for every exam question, you should always have the definition and any graphs that you need to know, and also need to be able to know how to link it from one topic to another as well. So we'll start off with this part here. So this is end diastolic volume. Your heart is basically full to the max. There's about 120 milliliters of blood in your left ventricle. And it's ready to contract. When it starts to contract, the mitral valve closes. When the mitral valve closes, that forms your first heart sound, and it snaps shut. The reason why the mitral valve closes when you start contracting is because of how the mitral valve is basically, the anatomy of it is when you have blood, it pushes into the pockets underneath the mitral valve, and it basically shuts it closed, so then it prevents blood from, basically when the left ventricle is contracting, it prevents blood from going back into the left atria, preventing that black flow. And also, this is also a big problem during mitral regurgitation, because if your mitral valves aren't working properly, that means that then your blood will be going into left atria instead of the rest of the body, which decreases your cardiac output. So yeah, this is the start of your left ventricle contraction. And the left ventricle, let me just explain this graph first. So your left ventricle volume is on your x-axis, and your left ventricle pressure is on your y-axis. So at the start of ventricular contraction, the pressure isn't that high. It will probably be around 10 millimeters per mercury. And then basically what the ventricle needs to do is it needs to create enough pressure to open the aortic valve. The reason why it needs a lot more pressure is because the pressure in the aorta is about 80 millimeters per mercury, or in this case 75 millimeters per mercury. It was around 75 to 80 millimeters per mercury, and that's the pressure that it needs to overcome. Because if the pressure is low in the ventricles, then it can't push blood out, because the blood only moves from a high pressure to a low pressure. So the heart needs to create enough pressure inside the ventricles to overcome the 80 millimeters per mercury to open the aortic valve to push blood out. So when it does this, the mitral valve is closed. The aortic valve is also closed at this point, meaning that while the heart is contracting and increasing pressure, there's no movement of blood. So it's called isovolumetric contraction, because the heart is contracting, whereas there's no change in the amount of blood. The blood in the heart is still 120 milliliters, but the increase in pressure, the pressure is increasing because the muscle is contracting. And this only lasts about 0.05 seconds. It's a very short amount of time, but there's a time where the heart is contracting, but there's no movement of blood. When the pressure is increased to a certain level until it reaches about 80 millimeters per mercury or 75 millimeters per mercury, this is when the aortic valve opens, because the left ventricle pressure is increased above the aortic pressure, and that basically forces the blood to forces the aortic valve to open. And then that basically, once it bursts open, it basically causes a rapid ejection phase. So isovolumetric contraction was about 0.05 seconds. The ejection phase lasts a bit longer at 0.25 seconds. So the first third, it basically pushes blood very, very quickly. It's a rapid ejection phase. And then after a while, it basically slows down. So the last 2/3 is quite slow as the rest of the blood is getting pushed out. It reaches a peak, your systolic blood pressure. So your left ventricle and then your aorta basically match the same pressure. And then this will basically be your systolic blood pressure, because that will be the max that the aorta will reach as well. and then when it relaxes, then it will drop back down to 75, which will be your diastolic pressure, which will be your blood pressure during diastole, and this will be your blood pressure during systole. So that's what systolic and diastolic blood pressure means. So you reach the peak at 120, and then eventually, while the blood is moving out, then the left ventricular pressure will decrease, and then this is when ventricular relaxation will occur. So as soon as the blood, basically the pressure reaches a certain point, and the blood has stopped, and the heart begins to relax again, the backflow of blood basically closes and shuts the aortic valve. It basically shuts, and this is your second heart sound. And when your aortic valve shuts, wait, is this your? Yeah, so basically, so when your aortic valve closes, this basically means that the ventricular pressure is decreased compared to the aortic pressure. Because the aortic pressure is very high right now because you're pushing all that blood into it, whereas your left ventricular pressure is decreased because you basically pushed all that blood out. And your aortic valve basically closes, and then that backflow of blood is basically what causes the dichrotic notch, because it basically increases the pressure when the aortic valve is closed. And then you basically have a period where the aortic valve is closed and also the mitral valve is closed. So that means that there's no blood movement again, and basically your left ventricle is expanding and it's relaxing. And while it's expanding with no blood in it and relaxing, this decreases the pressure dramatically. Until it reaches a point where the pressure in the left ventricle is below the pressure in the left atria. And then when the left atria pressure is above the left ventricular pressure, this is when the mitral valve opens up again. And that was what causes the filling of the heart. So this is the relaxation period. So the isometric relaxation lasts about 0.15 seconds, where there's no movement of blood and the heart is just relaxing. And then this is your diastole, where the mitral valve opens and there's rapid filling at the first 1/3, rapid filling, and then eventually you have atrial systole, so your atria contract in the last 2/3 and then push that last bit of about 15 milliliters of blood back into the ventricles. And that's your relaxation phase. And this is the longest phase, so it's 0.55 seconds, the longest phase. And basically this whole pressure volume loop is basically one heartbeat. And the area of this curve is basically the work done, the stroke work of the ventricular muscle. So as you know from physics, like force equals, work equals force times distance. So this is a similar thing where this is basically how much the energy the heart has taken. So if you expand this graph, which we'll see in later on when we talk about preload and afterload, if you increase this graph, then that means that the work that the heart muscle is doing is a lot more. And if the heart is doing a lot more work, that means that the O2 consumption of the heart, because obviously it's working at a higher rate, is also increased. So this is basically stroke work, the area of this graph here. And then EDP and ESP, so this is your end diastolic point and this is your end systolic point. And as I said, relaxation. So also, I forgot to mention that in your ejection phase, only about 70 milliliters of blood is pushed out. And that means that your end systolic point, so this amount of volume left over in your heart after every heartbeat, it doesn't push everything out. Unless you increase your contractility, then you can push more blood out. But usually, this stays the same unless if your preload or afterload isn't changed. So that's your end systolic volume, that's your end diastolic volume, and obviously that's your stroke volume, 120 minus 50 milliliters. And yeah, so that's your pressure volume loop. And then we'll talk about the law of Laplace. So the uni loves having this random equations and that you just need to explain. So the law of Laplace is basically pressure, the pressure difference across the ventricular wall is equal to 2 times the ventricular wall thickness times the tension of the wall, ventricular wall tension. So the wall tension is increased when you actually, when the muscle actually contracts. So that's how you increase the wall tension. The wall thickness is also increased when you contract. So if it's like at rest, then it's quite it's not that thick. But when you when the muscles contract, then the thickness of the wall also increases. And it's divided by radius. So if the radius is decreased of the ventricle, then the pressure is also increased. So increase the radius, increase pressure, increase of wall thickness and tension, increase pressure, and then a decrease of these two elements decreases pressure, and a decrease of radius, or increase of radius decreases pressure. So that's the law of Laplace. And this is a slide from the actual heart lecture from the uni. And it basically talks about how that law of Laplace equation changes and how the pressure changes depending on the phase of the cardiac cycle. So in the first phase, in the relaxation phase, ventricular filling, which is also known as the relaxation phase, the radius and the tension is increased. So the reason why the radius is increased is because when you're filling the left ventricle with blood, then obviously that increases the actual space, the radius of the actual ventricle. The T rises because of the length-tension relationship. So as I mentioned before, if you're increasing the tension, if you're increasing the stretch of the wall, that increases the tension of the wall. So that's why R and T rises. First, P falls down. The reason why P falls down first is because the radius is increasing. But because the tension is rising, because of the increase of blood filling into the ventricle, this eventually causes the pressure to rise up. So that's why it says P first falls down and then rises up. Then you have the isovolumic contraction phase. So this is when no blood is being moved out of the heart, and basically when both valves are closed, and it's basically the heart is contracting but nothing's happening, it's just increasing pressure. So in this one, all that's been changed. So the wall thing is not changed because it's isovolumetric. However, tension is increasing. The radius is not changed, the wall thing is not changed, but the tension is increasing. Because the tension is increasing, this also affects the pressure. What you're trying to do in the isovolumic contraction phase is you're trying to increase the pressure that it reaches above 80 millimeters of mercury to open up the aortic valve. So once the aortic valve is open, so this is why you're trying to increase the pressure, and this is why pressure increases in the isovolumic contraction. Then you have the ejection phase, which is that long curve here, the ejection phase. At first, so when it contracts finally and the aortic valve opens, the wall thickness increases incredibly because it's contracted. Nothing really happens. Radius decreases obviously because when you're contracting, obviously you're pushing the blood out, so then the actual radius of the ventricle decreases. So if your radius is decreasing and your wall thickness is increasing, that also increases pressure. So that's why in the ejection phase, pressure is also increased to the systolic blood pressure level. So that's why it's steadily increasing on the y-axis, is steadily increasing. And then during isovolumic relaxation, so this is during this phase here, when the aortic valve closes and then the heart is relaxing, but there's no movement of blood. That's when the tension is decreasing because the heart is relaxing. So if the heart is relaxing, then obviously the tension decreases. The valves are closed and nothing else changes, so then the pressure is decreased. So this is the differences in pressure, and this is what explains why the pressure changes like the way it does in this pressure volume loop. And they'll be asking you to explain this in the exam. They might also ask you like a robot question as well on this fact as well. Okay, so we'll talk about the determinants of cardiac performance. So as I mentioned before about stroke volume, about preload and afterload, I've already talked about inotropy, so I won't mention it again in this part because it's exactly the same about contractility, how contractility is affected. But preload is increased when you have an increased venous return. So then the question is, how do you increase venous return? There's a few ways. So venous return is increased during inspiration. So this is known as something called a respiratory pump. During inspiration, your thoracic cavity basically expands. And that basically decreases the pressure inside your thoracic cavity. When the pressure inside your thoracic cavity is decreased, that means that your vessels aren't they're not compressed anymore. They're basically open once the thoracic cavity is expanded. So once the superior vena cava is been basically not compressed anymore, that allows more blood to pump into the right atrium. Because you have more blood and increased venous return, and also causing more blood to basically come from the pulmonary veins as well. So basically, during inspiration, you have increased venous return because there's more blood being pumped in. And because you have an increased venous return, that basically increases the amount of blood that's in the heart, and that increases your preload. Other ways that venous return is also increased is via hypervolemia. So if you have a lot of blood in your circulation, so we'll talk about this later as well. So if you have like factors like EDH and aldosterone, which increase they decrease the amount of blood the water that's excreted by the renal system, and it increases the volume of blood. That also increases your venous return, meaning that preload is increased. Skeletal muscle pump, so that's when you start like exercise, etc. It basically, the way the blood is pumped back in from, like, because it has to go against gravity, if you have skeletal muscle pump, so then when your muscles contract, it basically pushes the blood from your vessels in your extremities and basically pushes the blood back into your heart. So in that case, also the venous return is increased. And also sympathetic venoconstriction. So the sympathetic nervous system, also during exercise, it acts upon the veins, and then the veins constrict, and then because the veins constrict, it causes more blood to be pumped back into the heart. Preload is also increased if you have an increased heart compliance. So increased heart compliance, that basically means that how much the heart is able to stretch. So if the heart isn't able to stretch that much, if it's very restrictive, it's very fibrotic, which is the case during like myocardial infarction or ischemic heart disease, or during certain cardiomyopathies, like restricted cardiomyopathy. If it's like restricted, then that means that the heart can't stretch that much and can't allow that much blood to basically enter the heart. So if that's the case, then your preload will be decreased. But if you have increased heart compliance, if there's more blood allowed to come into the heart and stretch the heart out, that means that your preload is increased. Because your preload is basically your end diastolic volume. If you have a higher end diastolic volume, then your preload is increased. So in preload, your end diastolic volume, so usually it's about 120 milliliters, but if your preload is increased, then your end diastolic volume is increased. So here in this case, it's about 150 milliliters. However, your end systolic volume remains the same. Your end systolic volume doesn't change. Even though the heart is contracting, it has a higher contractility. It's using that extra contractility to push more blood out, but it has the same end systolic volume. In that case, increased preload basically causes the stroke volume to increase because there's more blood being pushed out. So for example, if it was only 120 milliliters before, now it's 150. If you work out the stroke volume, so it's 150 minus 50. So that means that your stroke volume is increased to 100 milliliters. So you increase about 30 milliliters. So that means that you have a greater stroke volume. And also, if as you know, your cardiac output is equal to stroke volume times your heart rate. That means you have a higher cardiac output. But what you need to remember, so as I mentioned before, the area of this graph is basically your stroke work, how much work your heart muscle is basically doing. So when you increase the end systolic volume, as you can see, the graph has been shifted to the right. So that means that the area of the graph has basically increased compared to where it was before. So because this has happened, that means that the heart muscle is like using a lot more energy to push more blood around the body. That means that your stroke work has increased. Nothing else changes, if you notice. So your afterload has not changed. So that means that the pressure that the ventricle has to overcome is still the same, around 80 millimeters per mercury. The ejection phase has increased because you're pushing more blood around. But again, the systolic blood pressure, so the highest pressure that it reaches is also the same, around 120 millimeters per mercury. And then also your relaxation phase is increased because there's more blood that needs to be filled up into the heart. So that means that your relaxation phase is also increased. But everything else pretty much stays the same. And then you have afterload. So afterload is your resistance that the ventricles must overcome. So afterload is increased by, as I said, aortic valve stenosis. Aortic valve stenosis is when the valves have been calcified due to like plaque buildup or atherosclerosis or other reasons. So when this happens, this means that the valve cannot open fully. So when when they need to open, they don't like open up to the max diameter, meaning that the pressure that has to overcome to allow the same amount of blood is also increased. The vessel elasticity, again, by atherosclerosis, if it's decreased, that means that the pressure is increased. Hypertension across the whole body, plaque buildup, sympathetic arterial constriction, and increased total peripheral resistance. So if the resistance is increased by if your resistance increases, that means that the pressure that it needs to overcome. So that means that your aortic pressure will be increased to something like 120 millimeters per mercury, when usually it's 80 millimeters per mercury. If it's increased, that means that the heart needs to overcome that. It needs to push at a greater force. It pushes, it can still open the aortic valve and push the blood out. So as I said, pressure needed to open the aortic valve is also increased. But then at the same time, that means that because your heart is working so hard to reach this pressure, that means that the amount of blood that it can actually push out. So if it's used up so much of its energy, so much of his like the energy and the contractile force just to reach that pressure, that means it does not have enough energy to push the rest of the blood out. So that means that the actual stroke volume, if the afterload is increased, the stroke volume is decreased because it doesn't have enough energy to push out the whole amount of blood that it had. So so that means that your end diastolic volume is the same, because if your preload is the same, that means your end diastolic volume doesn't change. Whereas in this case, your end systolic volume, has changed. So if your end systolic volume decreases when your afterload increases. And this also shows, like, so for example, the graph has basically shifted up and to the right. However, the actual amount of stroke work that the heart has to do has not changed. This is quite an important point, because even though that the heart has to work harder to overcome the pressure, it's moving less blood out of the heart. So that means that the actual overall stroke work is similar. And as I said, end diastolic volume remains the same, and cardiac output is decreased because the stroke volume is decreased. So for example, in this case, the end systolic volume is now around 70. So if it's 50, it's about 60. The end systolic volume is about 60. This is about 120. 120 by 6 is now down to 60 milliliters. So that's why your stroke volume has decreased. And this is just a simple image that I found on Google, just to explain a little bit better. Again, you need to know more about these in pathophysiology, but just it's a nice way to explain it. So your preload is how much blood is entering your heart, and your end diastolic volume. Your afterload is the amount of pressure that it has to overcome. So, for example, if this valve is smaller, then obviously there will be more pressure that the heart needs to overcome to get blood through this. So that's basically a simple way to explain preload and afterload. All right, so now it's a question. So at the end of which phase of the cardiac cycle does the mitral valve open? So it's at the end of this phase. Yep, so the answer is E, the end of isovolumetric ventricular relaxation. So if we go back to pressure volume, at the end of the relaxation, when the blood pressure, the pressure of the left ventricle drops below the left atria, that is when the mitral valve is finally able to open, because blood is able to move from the atria to the ventricle. Also, I think I mentioned before, it's good to mention again, that the atria are only primer pump, so they're not really responsible for most of the end diastolic volume. Most of it is rapid filling by just passive forces. And then at the end, at the last 2/3, about 15 milliliters, or about 20%, is when the atria contract, and then it pushes basically the last bits of the blood which are left in the atria into the left ventricle. So the mitral valve opens at the end of isovolumetric relaxation. It closes at the end of relaxation. The aortic valve opens at the end of isovolumetric contraction, and then the aortic valve closes at the end of the ejection phase. All right, so now we'll move on to cardiac reserve and heart failure. So one of the main things that you need to remember is that cardiac reserve is a ratio. I remember that when we had our physio seminar, we got a lot of, we got berated because we kept mentioning that cardiac reserve was like a parameter which measures how much like blood is left over. Something ridiculous like that, but you have to remember that cardiac reserve is a ratio. It doesn't have a unit because cardiac reserve is basically your maximum cardiac output divided by your rest cardiac output. So it's not how much blood is left over, etc. It's basically a ratio which determines the max CO divided by rest CO. So obviously, if you're divided by the same units, then it cancels out. So then it doesn't have a unit. Why the cardiac reserve is important? Because it represents the heart's pumping capacity. So if athletes will basically have a higher cardiac reserve, whereas patients with heart pathologies will have a lower cardiac reserve. The reason why we need to know this ratio is because when the cardiac output is increased, or the body's demand is increased, will the heart be able to cope with that basically? So, for example, this is important with people with heart pathologies, because if a person with heart pathology starts to exercise, and the heart does not have enough cardiac reserve to basically able to provide that demand, which then eventually will cause heart failure. This basically shows it in this graph here. So then, if your workload, so the workload basically is the same as saying your actual body demands. If it increases to a certain extent, eventually your heart won't be able to cope and cause heart failure. Whereas someone who has a higher cardiac reserve, so for example, an athlete's heart, they're able to last a lot more time with a higher cardiac output before eventually they also cannot overcome the workload and their heart will fail too. So a normal person, cardiac reserve is about 3 to 4, and athletes is about 5 to 6. I think in the lecture it says just overall cardiac reserve is about 4 to 7. It can also be in some textbooks, it also says there's percentages. So I think in guidance it says something like 300 to 400%, and in athletes it's like 500 to 600%. However, I think the uni doesn't want it in percentages; they just want it as just like this. You also have different other ratios. So you have the coronary reserve, which is your maximal coronary flow divided by your rest coronary flow. This is actually your limiting factor. So if your coronary reserve is very low, no matter how high your cardiac reserve is, this is your limiting factor. If your coronary reserve is low, it doesn't make a difference. And we'll discuss this more when we talk about coronary circulation. You also have your chronotropic reserve, which is basically the max heart rate the heart can reach divided by your rest heart rate, which is again around 3 to 5. And you also have your volume reserve, which is your max stroke volume divided by your rest stroke volume, which is about 1.5. The main important ones is basically your cardiac reserve and the coronary reserve. You also have a parameter known as the cardiac index that you need to know. The cardiac index is also another parameter which basically lets doctors know how well the heart is functioning compared to the actual size of the individual. So obviously this is the case, for example, for obese patients. So if they have a very large body surface area, then their cardiac index will be a lot lower. The normal cardiac index is about 2.6 to 4.3 liters per minute per meter squared. And if it falls below 2.2, it's a useful marker which shows that the patient may be in cardiogenic shock and the heart isn't able to basically cope. So now we'll talk about heart failure. So heart failure is basically the heart isn't able to pump enough blood to supply the demand of the body. It's the inability for the heart to pump sufficient amount of blood into periphery, a normal venous return. The heart failure can actually be divided into different categories, and I'm pretty sure that you learn more about this when you study pathology, but you need to know this for the physio exam too. So it can split into acute and chronic. So acute heart failure, so it happens quite rapidly, and chronic, it happens over a long period of time. And you also have compensated and decompensated heart failure, which I'll discuss later on. And then it's also split into left versus right side heart failure. So it's either the left side fails or the right side fails, or you have something called biventricular heart failure. Left-sided is mainly caused by ischemia, hypertension, aortic stenosis, or cardiomyopathies. So, for example, ischemia causes necrosis of the heart muscle, meaning that it basically um, pump blood, or the force of contraction will be decreased, because if you have certain parts of ischemia, then obviously the fibrotic parts aren't like working contractile fibers anymore, so it can't contract at the same force. Hypertension, if the afterload is increased, also like hypertension, aortic stenosis, if the hypertension is increased too much, that means that then the blood can't pump as well, and not enough blood can be pumped out if the pressure is increased too much. Cardiomyopathies, so you have different types of cardiomyopathies. You have restricted or dilated. Restrictive is when like the heart muscle basically becomes very fibrotic again, so then again it can't like pump enough blood. Dilated is when it gets super dilated, and due to the length-tension relationship, if you have too much stretch, eventually then it can't push at the same force as we discussed before. So this basically means that the left side can't pump enough blood to meet the demand, and also demand the same amount of venous strength. So the same amount of blood is still returning to the heart, but it can't push it. It just starts pulling inside and causes congestion. And this congestion is basically, so for example, if you think about blood is entering the left side via the pulmonary veins from the lungs, this basically causes congestions in the lungs, because it's basically blood can't come into the pulmonary from the lungs anymore from the pulmonary circulation, meaning that it will just be a backflow, and then the lungs will start being filled and pooling with blood, and then this will eventually cause edema. And basically edema caused because the stasis of the blood in the arteries, it causes because of the pressure, it causes the water to flow out of the arteries, and that causes edema. And then basically because of pulmonary congestion, that causes dyspnea, so difficulty in breathing. And it also causes intra-alveolar hemorrhage, so bleeding in the alveoli, due to the pulmonary congestion. So that's like the main symptoms. So if you see a patient who you suspect has heart failure, to identify if he has left-sided dyspnea without the other right-sided symptoms is usually how you figure out it's left-sided heart failure. And left-sided is actually more dangerous because obviously your left side is responsible for your systemic circulation. So if you don't have enough blood going around the body, especially in the brain, it's actually quite fatal. Because of low perfusion to your other organs, you have activation of the RAS system, which I'll explain in the next slide, which is known as your renin-aldosterone or angiotensin-aldosterone system, due to low perfusion to kidneys. And this also shows a wide array of symptoms which correlate to left-sided heart failure. And then right-sided is mainly caused by pulmonary congestion. Right side, so if you think about it, that the right ventricle has to push blood into the lungs. If the pulmonary artery and circulation is all congested with blood, they can't push blood where the pressure is already high, and then the pressure keeps increasing. That means that the right ventricle will basically not be able to push blood, and then the blood will stop pooling the right side. And that means that then the blood can't reach the left side because it's just been restricted. So right-sided heart failure is basically caused by pulmonary congestion. But pulmonary congestion is usually caused by left-sided heart failure, so this is known as left-sided heart failure, like right-sided heart failure caused by left-sided. Always caused by chronic lung disease, and this whole thing is called cor pulmonale. So cor is, I think, Latin for heart, and pulmonale is obviously Latin for lungs, and this is the term which is how the lungs cause right-sided heart failure. And the main symptoms for right-sided heart failure is pitting edema. So if you have, if the blood can't go back into the heart, into the right atria, that means it will start pooling in the venous system. And once it starts pooling, especially in extremities, if you look at a patient with right-sided heart failure, at their legs, if you look at the calves, basically they become proper swollen. It's because water is basically being pushed out of the venous system, and it's causing edema in the legs. And it's basically called pitting edema. It's because when you push down, it basically it leaves a pit, and that's one of the diagnostic features of right-sided heart failure. Another symptom is the jugular vein distension. So that means that your jugular vein is basically distended because there's more blood in there. And it can also cause hepatosplenomegaly, again because of the backlog of blood left in the hepatic vein. and also edema. So now, how do we return cardiac output back to normal? So heart is failing, and there's not enough blood being pushed around the body. Like how do we increase the cardiac output so that it returns back to normal? So obviously we know that cardiac output is equal to stroke volume times the heart rate. So we can either increase the stroke volume or the heart rate. So that's basically one way that we can increase the cardiac output. So to increase both of these, we can activate the sympathetic nervous system. So this is done via the baroreflex. So basically the stretch receptors in the carotid sinus, they're able to detect that there's a drop in blood pressure. This drop in blood pressure basically decreases via herring nerves, I believe, decreases the firing of the parasympathetic, so it inhibits the parasympathetic nervous system, and it activates the sympathetic nervous system. And as we know, the sympathetic nervous system increases the heart rate and also increases contractility, and this is one way to increase stroke volume and also essentially cardiac output. We can also activate the renin-angiotensin-aldosterone system, which is basically this system here. So basically low perfusion to the kidneys actually causes the stretch receptors basically detect that there's a low blood pressure in the renal artery. The reason why the renal artery is so heavily regulated, because I don't know if you've studied kidneys, you should have. I think you've already had a seminar on it, but basically the kidneys need to maintain a steady glomerular filtration rate to maintain that enough toxins and all that everything's basically being filtered at a steady rate. Because if it's decreasing, that means that you increase other metabolites and they get left over in the blood. So that's why very small changes in blood pressure are detected heavily by the kidneys, and it's the kidneys' job to make sure that blood pressure is always and blood flow basically is always maintained. So there's low perfusion. To increase the perfusion, you need to start constricting and increasing the blood pressure. So that means that the flow is still maintained. So basically, stretch receptors in the juxtamedullary apparatus, they basically detect that there's a low blood pressure and low glomerular filtration rate. This causes renin to be secreted. Renin basically acts upon a substance called angiotensinogen, which is synthesized in the liver. Angiotensinogen gets converted to angiotensin 1, which then gets converted to angiotensin 2 by the angiotensin converting enzyme, which are located in the lungs. So they go through the lungs and they basically get converted to angiotensin 2. And angiotensin 2 is then a very potent vasoconstrictor. So angiotensin 2 is actually known to be even almost 1,000 times more potent than adrenaline at vasoconstriction. So angiotensin 2 basically causes the blood pressure to increase. It also acts upon the adrenal gland to release aldosterone, which is known as the mineralocorticoid, which increases the sodium retention and the water retention in the kidneys. So less sodium and less water is basically filtrated out, and there's more water in the actual circulatory system. So it means if there's more water, that means that if there's more hypervolemia, the blood pressure is also increased. It also works on by releasing vasopressin, or ADH, which increases the amount of water, or it decreases the amount of water secreted as well, increases the blood pressure in that way. So this is how the renin-angiotensin-aldosterone system works. So if you're increasing the blood pressure, if you're increasing the amount of volume of blood in your circulatory system, that increases your preload. And as we discussed before, increasing the preload increases the stroke volume, and then thus that increases the cardiac output. So these are the two ways that how the body reacts to heart failure. Another way, if you have chronic heart failure, is myocardial hypertrophy. So the heart muscle isn't able to, or cardiomyocytes, they don't have stem cells, so they're not able to make more cardiomyocytes. The only way they can do, they can allow more increased stroke volume, is by remodeling of the cardiomyocytes. So different stress signals are being sent in the cardiomyocytes, which increase the protease synthesis and basically mean that there's more fibrils, etc., and actin filaments and myosin heads, which mean that it basically causes the whole heart muscle to basically hypertrophy. So if you have hypertrophy of the heart, then that obviously means that the muscle is stronger, and it can cause a much stronger contraction when the action potential comes. So if you have a stronger contraction, that means that there'll be a higher stroke volume. That also increases cardiac output, so you can return cardiac output back to normal. However, this is also, like, all these systems is good in the short term because it increases cardiac output temporarily, but eventually all three of these actually cause a vicious cycle, which actually cause the heart failure to become worse, and that's known as heart failure decompensation. So if you have overactivation of the sympathetic nervous system, that means that because your heart rate is increased and also your contractility is increased, that means that the oxygen that the heart actually needs is also increased. Like the amount of oxygen that the heart needs is increased. And if you have heart failure already, that means that not enough blood is being pumped through to begin with. So if there's not enough blood that's being pumped through the coronary arteries to meet the demands, then obviously that will cause even worse one, because then that will cause ischemia, and that will cause even less blood to be pumped out, and that will mean there will be less blood pumped through the coronary arteries, meaning less blood will be pumped out. So there's a vicious cycle which causes the heart failure to get worse. And this is the case again with the renin-angiotensin-aldosterone system. If you increase preload and afterload, you're increasing the contractility and also increasing the afterload. That means that the amount of energy that the heart needs to basically have is increased because there's more oxygen consumption. So again, if you have increased energy outcome, there's not enough blood being pumped through the coronary arteries. That means ischemia, etc., would occur, and that will decrease again the amount of blood that's being transported. And also with myocardial hypertrophy, because you're increasing the thickness of the wall of so it's not making new cardiomyocytes. What you're doing is increasing the thickness. So that means that the actual volume of the ventricles also decrease. That means that there's actually less blood. So during diastole, there'll be less blood filling into the heart, and there'll be a lower end diastolic volume. Meaning that, and then eventually a lower end diastolic volume means that there's less blood being pumped out. That means that decreases stroke volume. If you decrease stroke volume, that means that there'll be less blood pumped again through the coronary arteries. And because the actual muscle itself is also thicker, that means that there'll be less oxygenation throughout the whole muscle. And obviously during high heart rate, the muscle won't be oxygenated enough. And then if this happens again, this will cause necrosis, ischemia, etc. And eventually this again will lead down to a vicious cycle, which will cause the heart failure to get worse, basically. So this is known as heart failure decompensation. I hope that was clear for you guys. So then we'll move on to coronary circulation, which is linked to it. Because your coronary circulation plays a major part. It's your main limiting factor for your heart. If you don't have a good coronary circulation, then no matter how strong your heart is, then you'll still cause ischemia and won't be able to deal with the cardiac output. So this is just a brief anatomy of coronary circulation. As I said before, it splits at the aorta, the right coronary artery, left coronary artery. You don't really need to know this for the physiology exam, but you just need to be aware that this exists and which side innervates what side, and just brief anatomy, basically. They're not going to ask you to draw every single branch like they would in anatomy, but just make sure that you're aware of this. So coronary arteries. So the actual endocardium and the myocardium is only receives about 1/10 of its nutrition from the actual blood that is in the actual heart itself. So that means that it actually relies primarily on the coronary artery circulation. So that means that the coronary artery blood flow is extremely important. And then to make matters worse, during systole, so when the left ventricle is actually contracted, because it contracts at such a force, it causes the intramural. So if you remember from anatomy, this is your epicardial and subendocardial arterial plexus that is in between the cardiac muscle. Because the left ventricle contracts at such a force, it actually compresses these arteries, and it basically stops the blood flow completely. So during systole, during ventricular contraction, you have no blood flow reaching the heart muscle at all. So that means that all the blood flow, when the heart, how the heart gets the nutrition, is only during diastole, when the heart is relaxed. So that means that the coronary blood flow has to be heavily regulated, because it's so important to ensure that enough blood and therefore oxygen is reaching the cardiac muscle at all times. Because it only has one moment, because there's literally a time where there's no nutrition being reached to the cardiac muscle, because during contraction it's compressed. So So they make sure that coronary blood flow, there's no problems to coronary blood flow during diastole, and that max amount of O2 is being extracted. So that's why like oxygen extraction at rest is max. There's almost like 80 to 90% of oxygen from the arteries is actually extracted from the coronary arteries during diastole. So yeah, so this is just a point. So coronary blood flow is about 150 milliliters per minute, which is about 5% of the cardiac output. So it's quite a lot of the cardiac output. And then you also have to think about the oxygen demand on cardiac muscle. So you have to, that's why like the coronary blood flow regulation is so important. So how do we maintain the coronary blood flow? So the only way to maintain coronary blood flow, because the oxygen extraction is at max, you can't increase the amount of oxygen being extracted. There's no way to do that. So the only way to increase the amount of oxygen that you're reaching to the cardiac muscle is to increase the coronary blood flow. And the only way we can do that is by dilating the blood vessels. So how do you dilate the blood vessels? So the main regulator of coronary blood flow is the local metabolic effect. So this local metabolic effect is in all circulation around the body, all organ systems, is where when there's a tissue which is has a high oxygen consumption and has a very high metabolism, it'll be releasing a lot of metabolic products. One of these metabolic products is adenosine, which it's broken down from ATP. So ATP goes to ADP to AMP to eventually adenosine. Obviously CO2 from respiration, lactate from anaerobic glycolysis, and the potassium ions and prostaglandins also cause vasodilation. These are all metabolic products, which basically, because when the heart is working at a very high rate and the metabolism is increased and it's releasing all these metabolic products, these metabolic products then affect the coronary arteries and they basically cause vasodilation of the coronary arteries, which then increase the coronary flow, which increase the amount of oxygen supplied to these tissues, basically. So this is the main regulator. Is basically, so if the heart isn't working that much, then the amount of metabolic products that it produces will be less, meaning that the vasodilation will be less as well. So this is the main regulation of coronary flow. There's also the nervous effect, but it's not that important. So the indirect effect is basically secondary changes to coronary blood flow. But again, this works via the local metabolic effect. If there's sympathetic nervous system stimulation, you're basically increasing the heart activity. This means that the metabolism is increased, meaning there's more metabolic products being released. And then that basically causes local blood flow vasodilation because they're vasodilators. And then you also have the direct effect. So you have alpha adrenergic receptors, which usually mediate constriction, and beta adrenergic receptors, which usually mediate dilation on the vessels. So there's more beta receptors on the intramuscular vessels, so these ones here, and there's more alpha receptors on the epicardial vessels. However, this is not that important because whenever actual direct effect of the sympathetic nervous system affects the vessels to reduce the coronary outflow, because the oxygen consumption is high anyway, the metabolic control overrides that. And this is the case in a lot of different cases because, for example, during exercise, when the sympathetic nervous system is activated, it causes the vasoconstriction of your blood vessels. This also causes vasoconstriction of your skin, your skin circulation. So that means that first your skin blood vessels would be constricted. Well, obviously we know when we do exercise, our skin is red. The reason for this is because of the local increased metabolism and all these metabolic products that basically increase the blood flow. Because the excess heat that's being produced, you need the vasodilation in your skin. So that's why your skin appears red because of this local metabolic effect. Because it basically causes vasodilation, even though the direct effect is the constriction of these vessels. And then also this brings us to ischemic heart disease. So obviously ischemic heart disease is caused by a abruption of the coronary vessels in some way. So as I said before, your coronary reserve is equal to your maximum blood flow, coronary flow, divided by your resting coronary flow. And a reduction of coronary reserve, so it's a very important parameter or ratio, which can lead us to believe, so if it's a low ratio, it can actually indicate that the person will most likely develop coronary heart disease or myocardial infarction. So it's quite an important ratio to know. a diagnostic purpose. So myocardial infarction is the most common of ischemic heart disease. So ischemia basically is like the lack of perfusion, basically. So myocardial infarction is actually the infarct. So it's when necrosis actually occurs. So it's due to atherosclerotic plaque within the coronary vessel with thrombosis. So there's a plaque that forms on the coronary vessel, and because of the rush of blood flow or other factors, it causes basically the thrombus to like embolize, and that basically causes complete occlusion of the coronary artery. And this can be due to also, so this is the main reason because of the atherosclerotic plaque, but it can also be due to, for example, coronary artery vasospasm, emboli, or vasculitis. And basically causes subendocardial necrosis, and this subendocardial necrosis is seen on the ECG as this ST segment depression. So on your ECG, the ST segment is depressed, and this is one of the main ways how you're able to see on the ECG if someone's like having a heart attack, basically. And you also have angina, which is also ischemia. Basically, you have 3 different types. You don't really need to know this for the physiology exam, but I thought I'd just add this in. You have 3 types. You have stable, which means that about 70% of your coronary artery is occluded. And you're basically not able to notice like stable angina unless you start doing exercise, and then you'll start feeling heart pain during stable angina. You also have unstable angina, which is a rupture of a plaque but incomplete occlusion. So it's the same as myocardial infarction, but it's not occluded completely. So this causes it unstable. And this is when you feel pain when even at rest. And you have Prince mentor, which is basically coronary artery vasospasm. But again, you don't need to know angina for the exam. The myocardial infarction is enough. So then this is the question. Which of the following changes will cause an increase in myocardial oxygen consumption? Yep, so the answer is D. It's increased side of the heart. So decreased aortic pressure will decrease your afterload, which means that the heart doesn't have to work that hard, meaning that won't increase myocardial O2 consumption. Decreased heart rate, again, if your heart rate is decreased, then obviously the heart isn't working that hard, so that won't increase your O2 consumption. Decreased contractility, again, same reason. However, this is the only one that might confuse some people. So increased influx of sodium during upstroke of the action potential. Even though the upstroke influx of sodium will cause an increase, like the strength of the action potential will be increased. It doesn't have that much of an effect on myocardial O2 consumption compared to the actual increased size of the heart. Because if you have if your heart size increase, obviously there's more oxygen that the heart needs. Yeah. And then we'll move on to question 25, the specific features of cardiac metabolism. So there's not much you need to know for this question. It's basically you need to know that the main energy source is fatty acids. So about 70% of the energy source that the heart needs is done via beta oxidation. That's how it receives its ATP. If it's working very hard under increased function, it actually undergoes anaerobic glycolysis as its source of energy. This can be problematic because it can lead to acidosis. However, because lactate is one of the vasodilators, it actually can be a good thing because the lactate can actually cause vasodilation, which means that more oxygen can be, basically the coronary blood flow can be increased and more blood will reach the cardiac muscle, meaning that it can undergo aerobic glycolysis in that case. And also this is also bad because anaerobic uses a lot of glucose, and as you know that glucose is one of the main or the main energy source for blood cells. So if you don't have enough glucose left for blood cells and also the brain, then obviously that's a bad thing as well. So you need to make sure that the blood or the heart is undergoing like normal aerobic or beta oxidation of fatty acids. Under ischemic attacks, ATP is broken down to adenosine. So ATP, as I said before, ATP to ADP to AMP. Broken down to adenosine, and then the adenosine is actually able to leave the cell. This is a good thing because it also is a coronary vasculator, increased flow. However, if you have a ischemic attack, that means that your blood cells need to be repaired, your tissue needs to be repaired. So if you don't have enough adenosine for DNA synthesis and tissue healing, that could increase the external necrosis, which is obviously a bad thing. And then we'll just move lastly onto regulation. So I've talked about regulation across the whole lecture, but just to put into one slide, your regulation of your heart parameters is split into two. So you have your intrinsic regulation, meaning that how the heart regulates itself, and then you have extrinsic, which is from your autonomic nervous system. So your intrinsic regulation is via Frank-Starling and your frequency effect, and your extrinsic is your semi-membrane nervous system. So this was actually a question in one of my friend's exams. So I think Novakova asked, what are the 5 ways that the sympathetic nervous system affects the heart? And you need to know all 5, because a lot of people think it's just the contractility and the heart rate, but it's also like 3 other factors. So obviously positive inotropic, so increases the contractility, increase the heart rate, chronotropic. Dromotropic is the conduction through the AV node, so the sympathetic nervous system increases that. Biohomotropic is actually increases the excitability because it reduces the urethral membrane potential, so it increases the excitability of the conduction and the action potentials. And then also I talked about the lusitropic effect, meaning that the rate at which the heart can relax to increase the contracted as well. So it increases the lusitropic. So these are the 5 ways that the sympathetic nervous system, and this was actually a question that was asked in the final exam. The 5 ways that how the sympathetic nervous system affects the heart. And also you have the parasympathetic nervous system. So the way it affects is that it has a negative inotropic, chronotropic, and dromotropic effect. And one thing to note about the parasympathetic nervous system, sympathetic nervous system has beta adrenergic receptors, beta 1, all over the heart, whereas parasympathetic nervous system, the muscarinic receptors, the acetylcholine muscarinic receptors, are only on the atria. There's no muscarinic receptors on the ventricles. So it does not affect the ventricles in that way. But the way it works is that it basically does the opposite. It basically does the opposite sympathetic. So it also provides negative inotropic in that sense. So yeah, I think that was the last slide. Yep, so that was the end of the lecture. So I'll be taking any questions, if any of you have any, if hopefully it was all clear and you understand it a little bit better. You can also ask me, like if you send me like a message after the lecture as well, you can just send me a message of any questions that you might have or any topics that you have difficulty understanding. I would really appreciate your feedback. So if you actually take out your phone, the camera app, and you hold it up to this QR code, it'll actually link you directly to the feedback form. So we really want your feedback to like how these like online seminars, how would you want these online seminars to go, if they're helpful or not. If you want to change like the scheduling or anything like that, then I really want your feedback for that. But yeah. So it doesn't seem like you guys have any questions, so I think I'll just leave it with that. So hope you guys are staying safe in this quarantine period and healthy, and hope good luck for your exams.